guys, and welcome to this month's tutorial for StemBox. This month we're learning about aviation and aerodynamics, specifically the 4 forces of flight: lift, weight, drag, and thrust. So we're just gonna get right into it today. Instead of doing an usual unboxing, we're just gonna show you how to fold the paper airplanes and then how to set up the different experiments that we're gonna do today. So in our box, we have 4 different airplanes for you to look at. We have the Dart, the Stella, the Catalyst, and the Steminator, in increasing order of difficulty. And we also have a Bernoulli's principle experiment for you to set up today. So that's gonna require the 2 balloons in your box. You're gonna have to find something like a pole or a broom to hang them from. We've provided the string for you, and we'll show you how to set that up properly because it can be a little confusing. And then we'll show you how to calibrate your experiment and get set up and start running your scientific method. Sound good? Sounds good. All right. So to get set up for the Bernoulli's principle experiment, you're gonna need your balloons. Caroline and I are ready with them. And we're gonna blow these up. We want them to be about the same size. And then we're gonna have our string on hand and something to hang them from. So something like a pole maybe. All right. You ready to blow these up? Yeah. Now that you have your balloons tied and secured, we are going to tie them to our wooden dowel. For you at home, that might be a broom, so you might need a friend or your parents to help you out with this part. So we're just gonna tie these so that the balloons themselves end up being, they really like us, are gonna be about 3 inches, 6 inches apart, 3 to 6.
Like that?
I think that's a good distance.
And the same
length,
okay.
Yeah, the same height. Same width apart, same height. And if they're a little staticky like that, it might help to get a dryer sheet and like rub them with it because they get rid of the static. So if you have some technical difficulties with the static on your balloons, just let them like work it out, play with them maybe a little bit, because over here just now what you missed is that we had some static, and that meant the balloons didn't want to go near each other. So just like kind of roll them around, get rid of the static, use a dryer sheet. And now that our balloons have calmed down, we have 2 kinds of straws in the box, and we want you to figure out which straw might be better for this experiment. Another property of aerodynamics that you will come to be aware of in the course of this experiment. So we're just gonna start with our skinny straw. So basically you're going to blow between the 2 balloons as so. Like that. So what you wouldn't expect is the balloons to go together. You would expect that they would blow apart. Do you want to try it?
Sure. So how do I
You just have to line up your straw so that it is not between, but behind. Ooh, that's static.
Calm down.
Yeah, they're out of control. All right,
Okay,
we're
so
good.
not in between, but behind.
Blow between them, but don't put your straw physically between them. Bernoulli's principle at work. That's awesome. I love this experiment. Okay, cool. And then you can try it with your big straw. We'll let you figure that out. And then tell us what you think, like which straw worked out better. Have you tried thicker straws, skinnier straws, stir straws? There's so many straws in the world.
So why does that happen?
That happens because Bernoulli's principle states that if the speed of air is flowing faster, the pressure above it is lower. So there are pressure forces acting on every side of this balloon, but by speeding up the air that's moving between these balloons, we're decreasing the pressure between them, so the forces on the left and the right of these balloons are still the same and pushing them together.
Okay, cool.
Does that make sense?
So pressure decreases in between the balloons, but it stays the same on the outside, and then they come together?
Yep.
Cool.
Yep. That's that. So in our boxes this month, we have 4 different paper airplanes for you to fold. One of them, the Dart, has 2 materials for you to try folding with. The cardstock can be a little thick sometimes, so don't get too frustrated. It's totally normal. So we have the Dart, the Stella, the Catalyst, and the Steminator. And these are going an increasing level of difficulty to fold. So just watch the videos, pause where you need to, and then you'll be fine. So one of the forces we talked about was drag, and that means that we're gonna add some of that to our airplane by making a couple small cuts in the back of our wings, about like an inch, maybe 2 inches apart. And then we're gonna fold them up like this for these little flaps. And then that is our new airplane. In your box, you'll find that we've included some paper clips. These paper clips are a really interesting and fun way to learn about how weight might affect our airplanes. So we want to know when you put a paper clip on your plane and a different part of the plane, maybe like at the nose, in the middle, or the tail, how that might affect the flight of your plane. Is it better? Is it worse? So instead of just putting 1 paper clip on the nose, maybe, what's it like to add 2? Or what's it like to put 3? And you can spread these weights out all over your plane. We want to see it on the back, maybe one in the middle, and we want to know what this does to the pattern of flight. That's what the back of your protocol is for, that big grid. We want to know what it does to the plane. So make sure you record your results and send them in. We would love to hear how this went for you and what kind of crazy variables you can come up with at home. So in your box, you also have a roll of masking tape. This is going to serve as your runway. I'm gonna do this for a short scale on the table, but when you're at home, you're probably gonna wanna stretch this down like a long hallway, a big open room, maybe on the sidewalk. But for our purposes today, I'm just gonna lay out some tape in a straight line, like this. And I'm gonna pretend that I am throwing airplanes along this teeny tiny line. So the first step in doing any experiment is calibrating your equipment. So this means we want to make sure that our equipment is not affecting any of our test results if we add variables. We want to know that our equipment is consistently and constantly performing the same every time. So for us, that means that we're going to be calibrating our throws, which means that we are going to do 3 throws, and say my first throw ends up here. And then I do a second throw, which ends up kind of short here. And then my third throw falls somewhere over here. Now, between these 3 throws, I want to know what my average length of throwing is so that if I add something different, I know that it's what I added to the plane that's changing the flight. So actually, my average is probably more in the middle of the 1 and the 2, close to 3. So this is now my standard, or my average. So when I add new variables to my plane, I can see that if the plane is going further than my average and landing here, that I did something to make it fly better. If I land short of it, I did something to the plane that makes it fly worse. So this is how we're gonna do it at home. On the back of your protocol page, there's a grid. We want to see how far these different variables will take your plane, how short they make them go, and you can use this tape to track those changes. So every time you throw something, just make sure you make a little annotation as to what was the change, like 2 paper clips. And then you can translate that back into your grid by saying this did 1st, 2nd, 3rd, or 4th place in terms of the variable additions for this different type of plane. So now we know how to fold our airplane, set up our experiment, and we're good to go. If you have more questions, check out our other videos. We have a great interview with a Boeing engineer. And yeah, what else are we doing this month?
So when you share your results with us on social media using the hashtag StemBox, we are going to give away free year-long subscriptions for Most Creative, Longest Flight, and Best Variable.
Oh my God, are we crazy? Anyways, thank you guys so much for tuning in. We'll see you next time. This has been Keena and Caroline with StemBox, and we will see you later.
Bye.
There are 4 primary forces required for flight. The first one is going to obviously be lift. That's the force that goes up. It is